Welcome to Study Loop.
Okay, here I have drawn a model of refrigerator. In this refrigerator here, the refrigerator takes away heat from inside the refrigerator from the goods or the food that is kept inside the refrigerator and take this heat out into the room. And for this, for the transfer of heat from a cooler from a cooler surface or the cooler body to a hotter body, it requires some amount of external work to be done on it, and that is the electrical energy W. So depending upon how much heat can it take away from the food uh, per unit electrical energy that it consumes, we define the coefficient of performance of refrigerator, that is given as the amount of heat that it takes away from the food per unit amount of electrical energy that it consumes. All right, so now the heat energy that it throws away to the room is Q1, that is the sum of Q2 and W. So I can write W as the difference between Q1 and Q2. So let me write that this way, Q1 minus Q2. So let me arrange this in this form. So 1 upon Q1 minus Q2 upon Q2, bringing Q2 downwards. Okay. Now let us separate the fractions. So this will be 1 upon Q1 minus Q2 minus 1. Now for a heat engine, Q1 by Q2 will be equal to T1 by T2. So I can write this further as 1 upon T1 upon T2 minus 1. Okay. Now what we need to see is that if the room is warmer, it consumes more energy, right? Yeah, okay. So if the room is warmer, that is T1 is high. So if the room is warmer, T1 is high. So if T1 is high, so then this implies that T1 by T2 will also increase, will also become high. Now this implies T1 by T2 minus 1 as a whole also increases. Now, with this increase, of course, the coefficient of performance K decreases. If K decreases, that means W increases, right? So work to be done on the refrigerator is increased. So higher the temperature of the room, so warmer the room, more energy it consumes. Well, is it true? Oh, yeah, more energy it consumes. Okay, so this ends the answer.